Hi, my name is Pramod. I'm part of the CoinOp collection group, and what we do is we focus on preservation of old arcade technologies and boards. We do write some FPGA cores as well. And today, what I'm going to take you through is an overview of the Midway Z and Y units that I've been focused on for the past year or so. And the work was very extensive. It's inclusive of a working core um, for the Z unit and the Y unit, as well as a working CPU, which in this case it uses the TMS 34010 model CPU. And first of all, I want to start with the architecture of the board. So assuming you have the board, and I'm just through this video, I'm just going to whiteboard some stuff for you to follow along. And the first thing I'm going to do is try to convey to you what the architecture of the basic architecture of the board looks like. So at the heart of the board is the CPU. So usually when we take a look at boards, we start with the CPU component or the components. It could have multiple CPUs. In this case, the board does in fact have multiple CPUs, but we're only going to focus on the main one that drives the program and computing logic. So that's the CPU. So this is the TMS CPU, right? And basically, this is the heart of the system. Uh, the CPU also includes a GPU unit. Now, the GPU isn't really used in the overall system all that much. It's only used for the post screens. So when you see the screens pop up that show a picture of the board and it tests all the various memory chips and all that stuff, that's actually the GPU unit of the TMS CPU that is driving that. However, once it actually switches to the game, it uses another chip, a custom chip called U99, which is a so-called DMA chip. And the purpose of why they included this chip on the board is because the TMS CPU has 16 bits output and input. That is for getting data into the CPU and out from the CPU. However, this is not fast enough to drive the games that they wanted to do, or the program logic that they wanted to do, or the graphics that they wanted to make the games for. So they included this custom chip called DMA. Now, um, in the other units, the T unit, you may also see that there's another chip called DMA2, which is a successor to the DMA chip that includes more advanced routines, scaling routines, and also it uses a form of compression. It uses the run length encoding for its compression of the graphics, so it does all that stuff and does a little bit of scaling too on top of it. But this DMA chip is actually fairly simple. It includes a few pixel processing operations, the ways in which to draw the pixels, so to speak. And so we'll be talking a little bit about that later. So you have the TMS CPU right here. You have the U99 DMA. Now the DMA actually has 32 bits of output. It only outputs stuff. It does not take in any data like to write to, like uh, it doesn't output any data that you can read from, is what I'm saying. It only outputs data to memory. And so this has 32 bits of output. It inputs 32 bits from graphics. So graphics is an array of chips right here, array of ROMs, right? This is graphics right here on the side. Okay, so we'll call that graphics. On these boards, graphics are always in a series. They're always in an array series. So if you take a look at different boards for arcades and stuff, you'll notice that graphics has banks. There are banks in which they split up the graphics modules into, but they're also interleaved and intertwined, right? So they have arrays of chips that output a certain bit length each, and then on the bus they combine to form a wider width. And so that is 32 bits in from graphics here, right? So they have an array. Now on the Z unit, which is basically NARC, they actually have a quad array of chips forming the graphics. That means that each chip outputs 8 bits. However, they're quad interleaved, right? So there's 4 chips that combine to produce one singular output. So that's 32 bits. And on the Y units, actually they use 6-bit graphics. So there's an array of three chips that combine to produce 24, and from the 24 you can actually rearrange those bits to produce 32, and that will give you your 32 bits, basically output to the DMA. So the DMA takes the 32 bits in from graphics. So it's actually an interface. It's actually an interface to the graphics. It's an interface to the graphics, and it outputs 32 bits to memory. So there's a lot of different types of memory in the Williams systems. Let me go over some of them here, and let me just take a look here. So we have, let me just shift my whiteboard over a bit. Right there. Okay. So first of all, we have the types of memory, right? Okay. So first of all, there's something called video RAM. Now, this is not scratch space for video, but rather this is what you might call a frame buffer. Like, so this stores the literal pixels representation that you'd see on the screen at any given time. The pixels, the actual final pixels are 16 bits in length. And are composed of 2 different parts. So the first part is palette. ID. So palette ID is 8 bits. And the color ID is another 8 bits. So that's 16 bits for each pixel. Okay? And the array that it's stored in is 512 by however many lines there are for the game. So in some games, for NARC, there's 400 lines that it outputs, right? So it's going to have a 512 by 400 array, which corresponds to 16 bits in each address. So it's 16-bit addressing. And for some of the Y unit games, you have 512 by 256 max. Okay, so the games actually in the Y unit all have slightly different horizontal resolutions, but the memory array stays the same. So it's always 512 in length. It doesn't use all the 512 on each line. It'll use like 400. Or, I mean, 400 is pretty much what most of them use. Some of them use 410. Some of them use 396. There's slightly different variations in the horizontal length for each of the Y unit games. But even the vertical height is slightly different. This is the active height, right? Some of them are 256. Some of them are 254. It really depends on the game, right? But at the end of the day, you need to allocate 512 by however many lines there are for video RAM. Then there's another thing called color RAM. Now, color RAM is basically loaded at the start of the program, and what it contains is a list of palettes and their associated colors. Each object in the game, each object can contain up to 256 colors. So each palette must contain a max of 256 colors. There can be a maximum of 8K colors on the screen at any given time, right? Okay. So what the color RAM does is it stores at the start. You'll see it load, but at the start you'll see this type of RAM loaded up with all the possible palettes in the system and all the possible colors that go within them. So when we take each pixel representation, right? We take each pixel representation. We take the palette ID. That's one side of the address, and then the color ID. And if we look up these two, and we form an address in palette RAM, or color RAM rather, they call it in this system. And we can look up what color that is, and then we can decode that color and transform it into a color space, and then output it into RGB. Okay, so that's basically what color RAM is, and that is about 60. It's a 16-bit address, right? So it's 64K, right? Addresses for this colors. And then there's something called scratch RAM. That's also 64K, and it is basically your main RAM for the CPU to do its work. So this is indicative of, this is inclusive of the stack, right? So the stack, if you push things onto a stack, you pop things from it, that actually goes at the end of the scratch RAM space, and it goes downward, right? So in the TMS CPU, things go from higher to lower addresses, and as they get popped, they release them and they go higher, right? So your pointer goes up instead of down. So that's your scratch RAM. And then you have something called Bitmap RAM. Which I'll talk about in a minute. And then alongside of Bitmap RAM, you have something called palette RAM. Okay, so now Bitmap RAM and palette RAM are actually two different. They're two different things technically on the board. They work a little differently and they're composed a little bit differently, but at the end of the day, they combine together, right? So Bitmap RAM is actually going to be has a 32-bit pipe. However, palette RAM has a 16-bit pipe. Okay, so the 32 bits, this is 32 bits, and then it's 4 times 8-bit, right? And this is just 2 times 8-bit. Okay. Now, what's really interesting about Bitmap RAM and palette RAM is that if you have if you have an array of pixels, right? Let's just say, for example, what you can do is, or what the system actually does is, it reads 4 pixels at a time and writes 4 pixels at a time, always from DMA, right? So DMA outputs 32 bits, right? As I mentioned right here, it outputs 32 bits to this Bitmap RAM and palette RAM, right? Palette RAM. Right, it outputs 32 bits here, and it outputs, actually it outputs 8 bits here, and I'll tell you why in a minute. All right, so it outputs 8 bits here and 32 bits here. Now, what's interesting about this sequence of events is that each of these this 32 bits actually represents 4 pixels. Okay, so it's 4 times 8. Okay, 4 times 8 pixels. And what happens is these 4 pixels actually get muxed with this palette RAM entry, right? So you have a sequence like P B P B P B and PB, right? The P is the palette ID, the B is the color ID, right? That I showed you over here. Which is the same composition, right? Only the DMA, so the DMA actually has ability to write to video RAM. It also has ability to write to bitmap and palette RAM as well. And why are they different? So actually, in emulators that you'll see today that implement this system, you'll see all of this combined, right? So you'll see bitmap RAM, palette RAM, and video RAM all combined into one giant contiguous thing, and that's not how the system actually works on the real board, because in order to achieve this throughput, right, of writing 4 pixels at a time, you have to have something that muxes these together for this bitmap RAM and this palette RAM entry, and writes 4 pixels out to the thing. So there's a direct connection between this DMA and these actual memory chips. Now, what's interesting about the palette RAM is all the DMA has to worry about is writing these bitmap RAM entries in contiguous addresses, right? So you have address 0, 1, 2, and 3, for example, right? And so all it has to do is worry about the bitmap RAM side of it. The palette RAM side of it is actually a replicated value. So let's say you have a palette ID of 44, right? 44. So 44, what's interesting about palette RAM is that would be 2 successive 16-bit writes, right? Because you need to write 32 bits to cover all the 4 pixels, right? And what's interesting about how palette RAM is structured is if you write to this address and this address, that same value is actually going to be replicated across to this one and this one. So there's a concept of addresses that are actually linked together and replicate themselves to complementary addresses. So that's how the system achieved its high throughput. From a memory perspective, and that's one of the challenges that makes this very difficult to implement in an FPGA core. Now, from a computer or PC emulation perspective, right? So let's say you have a software emulator. I think it's a lot easier, obviously, to work with memory in a software emulator as opposed to an FPGA core, because in FPGA core, you have many different types of memory that you can possibly use, right? You can have, I'm sorry, in an FPGA system, you have many different types of memory which you can use. So like you can have SD-RAM, you can have block RAM, you can have SRAM, you can have like all these different types of things. And then you have pseudo-static RAM, you have DDR, you have like all these different types of things. And all these different types of memories have different interfaces, right? And they all have different speeds, and they all have different nuances when you try to access them, right? And so that's what makes this problem so difficult in an FPGA world, is that it's not computational power that's the limit here. It's actually the memory bandwidth that's the limit, right? And so you have to find a way to kind of get these writes done. So actually, in reality, instead of writing just 32 and 7 and just like replicating everything across, there's not really a concept of replication in an FPGA core, right? If you're using SD-RAM, right, there's not a concept of, oh yes, I'm going to write to this address and this is going to automatically replicate to something else, right? That's not really how it works, right? So you have to write those things either in burst, or you can write it one at a time. I mean, it really depends on what you're doing, right? But basically, this is one of the challenging aspects, of this system. And we'll get to that a little bit later, as well. So one more thing that is also part of the base architecture, besides memory, besides the graphics ROMs and the program ROMs, I also should mention about the program ROMs too. The program ROMs are usually an array of 2 or 4 chips, and that is actually a minimum of 512K, right? That you have to use to store your program ROM for the TMS. So if you're storing under 512K, let's say your program ROM is 256 or something, right? You actually have to pad that so it is 512. And the reason why you have to do that is because you see that the entry point for the program is located at the end of the 512K, right? So if your program is under 512, you have to pad it. You have to pad the beginning of it so that it fills up the whole 512. And so your program is actually allocating the entry point towards the end of the address space as opposed to the beginning, like in some other CPUs, right? So you'll see games like Smash TV, for example, and I think Total Carnage as well. Those are some of the smaller games on the spectrum. They take up under 512K actually for the program ROM. However, they have a bunch of padding in the beginning, and so the entry point's located at the end here. Now, what's interesting about the program ROM is that the CPU internally has a cache of 256 bytes. Right? And the cache is actually an interface to this program ROM, right? So every time some instruction needs to read from the program ROM or a new instruction needs to be fetched and decoded and all that stuff, it actually goes to the internal cache of the CPU first, okay? And if that item, that address is not located in that cache, what's going to happen is it's going to fetch a new series of 64 bits from the program ROM. So you need to account for this too in your memory model, right? Because all of a sudden now, I mean, from an FPGA perspective, I mean, we don't have to figure out what the issue is, with regards to the to loading it to memory. But from a ROM perspective, if you're working in an FPGA core, and you have all these ROMs loaded in SDRAM, you also need to think about that too, because now all of a sudden there's this 64-bit thing that's going around, and that can be going around hundreds of times a second. Who knows, right? Depending on what instructions are executed. So you need to account for that bandwidth too. So you have the 64 bits here, you have this 32 bits here from the graphics. You have this RAM going on, which this RAM is already pretty high. I mean, you can't really store all of it in block RAM, so you have to split some of it off into SDRAM, and the SDRAM is pretty slow, I mean, compared to block RAM. So that's also another source of headaches. So those are some of the things that are going on. Now, to add on top of this, there is yet another thing called the auto erase latch. Okay, and that's called U22, right? It appears as U22 on some boards. It is a PLD, okay? It's an Altera PLD, okay? And what that's responsible for doing is after things go from the video RAM to the screen, okay, this auto erase latch is responsible for clearing the line that just got outputted to the screen. Okay. Now, normally how I would handle that in an FPGA core is I'd have all this. You see this video RAM up here? I would have all of these. Oops. I'd have all of these. This video RAM here. I would have that all in block RAM. Let's say I was working on some really low end system, like it's 320 by 240, some really low res, right? I'd have all of that in block RAM. That's simple. I can do some auto clearing thing after it outputs pixels to a line buffer. So this system also has a line buffer, by the way. That's not included in this types of memory thing, but yeah, that's there too. That's also there. there's a line buffer that transfers data for the subsequent pixel of where the CRT guns are. And it loads them into a line buffer, and then from the line buffer, the CRT guns, there's a thing that looks up the color from the palette, and then outputs that to the screen, right? From a line by line basis. But what I would do is I would put that there, and as I output things to that line buffer, I would just erase them, right, from the from the block RAM. Easy, right? So it's so easy. However, in this system, you can't really do that, right? Because there's just not enough time. So there's something called, I don't know, some of you may be familiar with this, or maybe not. I mean, if you're not technical and you don't program these types of systems, but there are different phases in the video cycle, right? So there is like your active area. Right, this is the video. This is a video screen. This is your active area. This is H active. This is V active, right? And basically, there's a period after this called a horizontal blanking period, right? Right, and then there is an H sync period and all that stuff. But mostly we're talking about the H blank period. The H blank period is all encompassing of all those regions, like the synchronization area and that. And there's also a region below here, and it could be above here too. And it could be before here too. That's the porch. And then basically we're talking about the V blank area, right? Now, what these areas are is basically these are regions where you can do work. Okay, basically. So if you're on line 0, for example, right, and you're outputting line 0 to the screen, let's say, for example. So 0 is actually outputting to the screen, right? Literally, it's outputting. The CRT is loading up 0, line 0. You're going to actually be writing line 1 in this H blank period to this line buffer. Okay? And then if you're on line 1, now you're going to be writing line 2. And if you're on line 2, you're going to be writing line 3. Like, it's always one line ahead. Now, that could change for some systems, right? Like I've seen some systems that buffer 4 lines ahead or 2 lines ahead, right? So for example, you'd start, if you're outputting line 0, you're already outputting line 2, for example. And how that would work is you're always 2 lines ahead of the CRT guns, they call it. So you're always 2 lines ahead, so you have a buffer width of 2 times the number of lines that you have, right? You're like double the line space, right? So you're outputting already, you've already output line 1, you're outputting line 2, and then you're going to go to 3 when the pointer's at 1, and so on, right? So the only time you have to do this work is in the H blank period. So if you have a situation where you are outputting multiple lines, right, to a line buffer, you have to make sure that you can load the entirety of this line, right, into the line buffer before the CRT returns back to this area, the active area, and starts outputting stuff, right? Because then you have what's called overrun, right? You can't be outputting like the end of a line while the CRT is outputting that to the screen, because then all things will be screwed up. You may not get the whole line. I've been in situations where I've gotten half of a line or something. So all kinds of crazy situations can happen if you do that. Now, if you have these types of RAMs, like if you have this type of video RAM in an SD RAM, for example, you're probably not going to have enough time in this H blank period to output these pixels. I mean, especially if you're talking about 400 pixels, right? Or if you're talking about 512 pixels, right? You're not going to have enough time to output that to the buffer. You're just not going to do it. There's no way. There's no how. You cannot do it, right? It's just going to take too long, right? So the only solution, there's multiple possible solutions to this problem, but you can output multiple lines, of course, but then you have to bet that on average, you're going to come out ahead of the CRT gun. So let's say, for example, you can output 4 lines in 3 lines worth of time always, and you can end there, right? With maybe some spare or not, right? Well, let's say you're guaranteed that, then it makes sense, right? But if you're in a situation where it's constantly cascading against each other, you're not going to meet the time, and it's not going to work, right? Because eventually the CRT guns will catch up to you, and you're done, right? Basically, now your CRT guns are going to be ahead of what you're outputting, right? You're not going to output at a rate that is fast enough to cover what the CRT guns are doing, right? So you're not going to go ahead of it at any time, right? And so you have to figure out ways to do that, right? So that's that kind of strategy is something you have to really think about in this type of system, because it's a very high throughput system with a lot of memory and a lot of stuff going on at the same time. So in any case, this auto erase latch is responsible for erasing lines once they are outputted from a line buffer to the CRT. Okay, and that's another source of headache, right? Because if you're outputting lines at the same time as trying to erase them, right? You can't really. That's 2 different operations, right? One is a read and one is a write. You have to read from SDRAM and you have to write back to SDRAM. There's not like a mode in SDRAM where you can just simply, oh yes, if once I read this, just automatically erase this. Like that, there's nothing like that. You have to perform a write operation, and then before that, you have to perform a read operation, right? I mean, you can burst read, you can burst write, sure, but you can't really do them all simultaneously. You have to spend cycles to do the after effects and the before effects. Okay, so that's another source of headache, and that also eats up bandwidth too. Okay, so that's generally, and I'm not going to talk about sound in this because I haven't really gotten into sound all that much. I modeled an early version of the sound board. One of the soundboards. There are various soundboards in the system. I have like a bunch of them in my house. Like I'm telling you, there's like at least 4 or 5 different variants of a soundboard for these systems. Not to mention the T unit. So like there's a lot of different variants of them. So that's why I haven't like really gotten into sound. They all kind of share the same components though. Like there's always a 6809 on them. There's always there's always a 2151 on there. There's always, right? And then I think some of them use Oki for speech, and some of them use a CVSD for speech, right? Which is an older technology that used to be around to output speech samples, right? So some of them use that. Some of them use a newer thing. It really depends on the game you're working on. So that's why I really haven't gotten into that just yet. And the sound is pretty challenging, right? Because if you've ever seen one of these boards, you have you have the PCB, but the sound actually is a separate board that hooks in via this this cable. You have a cable, and then it has power that goes to it. There's a potentiometer that goes in there that controls the volume. There's all these different wires coming out of it. Like the way it interfaces with the main board is a bit weird. It interfaces over like this IDE-like cable, right? Basically, it's just a pain. There's nothing else to say about it. It's just a real giant pain. There is like, what's weird about it is there's not only like clocks that drive it, but there's software clocks that drive it too. So like the software actually outputs a signal that's used as a clock to do stuff in the sound. So that's also weird about it. And I implemented that based on schematics that I have, but I guess I haven't just had time to debug that and get that working completely because I was focused on the other main parts of the system. But yeah, that's sound in a nutshell. Okay, so let's talk about now the FPGA core parts of this. Like, how would one go about implementing this in an FPGA core? Well, that's the question, right? Ultimately, at the end of the day, when you take a look at the board and you take a look at the schematics, and the good part about the system is that um, all all the stuff that is a part of the system is very well documented, right? So there's like a bunch of manuals that I've read through. There's like a 600 or 700 page manual for the CPU alone. There's another manual for the architecture of the Midway units, the early Midway units. There's schematics for all the games, like everything that you could possibly want. There's working emulators, so there's a working model of an implementation of the system, right, available. There's an emulator, that supports it, either MAME or Final. I usually like to use Final Burn, but there's documentation on all this stuff. So I don't really have to go to the board to do stuff, right? To pull stuff off of there, or pull values off of there. I will operate the board. Like, I'll take a look at the speed of it, because that's what concerns me the most with this type of system, is the speed at which things are executing. It's not so easy because the resolution is very high. The amount of RAM that it takes to represent things is also very high. Everything is 16 bits. Everything is 16 bits in this system. The whole thing is 16 bits. So there's a lot of ROM that you have to read through. So there's a whole bunch of things that you have to do in order to figure out how to that'll have an impact on the speed of the overall system. Okay, so let me go ahead and start talking about different memory models, because the key issue here is memory. And I tried lots of different memory models to see what would work on the Mister, because the Mister has a limit, obviously, in terms of the BRAM space available. That's the thing that works against us a lot of the time. SD-RAM is also an issue too. The bandwidth is fairly limited for SD-RAM itself from a fabric perspective. But also, some people have dual RAM, some people have single RAM. Like, there's all different configurations that people can have. Some have a low amount, some have a high amount. The amount doesn't really matter all that much, but it's the fact that the bandwidth is so limited, that works against us, a lot of the time. So the memory models aspect of it is something that I've played around with for a few months, actually. I think I spent more time playing around with memory models in this system that will work efficiently, rather than actually programming the core, right? Because the core is pretty easy to put together once you have all the components. The CPU is a beast itself, right? So the CPU has issues, right? But then the other parts of the system, the memory, also have an issue too. So it's give or take, right? You have to figure out how to efficiently represent these things and have a decent throughput to perform the core operations and all that stuff. So it's really tricky to fit all this into one core. And so the CPU is a beast. So that was a lot of the time spent. I think that was like 3 or 4 months maybe to come up with a working CPU. And then after that, simultaneously, I started putting together the core for a NARC as well at the same time. But I want to say I got everything pretty much implemented in about 6 months. I want to say, like, the whole entirety of the system implemented in 6 months, and then I was doing bug fixes. But then I was playing around with memory models. So I spent like about half a year playing around with different sort of memory models, going into SD-RAM, going into DDR, and going all through these different motions and trying to figure out what's going to achieve the necessary throughput that I need. So from a memory models perspective, I've put color RAM. So this is BRAM. Okay, and BRAM is inclusive of color RAM, scratch RAM. Oh, and one more thing I forgot to also mention is CMOS RAM. In this types of memory. Maybe I should write that here. CMOS. CMOS RAM. CMOS RAM is used to store the settings of the system, right? So for example, if you go into the settings, if you go into the test menu and you start playing around with different settings, like some boards have, like, oh, the volume, right? You can control the volume, software controlled volume, right? Or you can do like the coinage, right? The dip switch coinage, or other settings like violence high or nudity or something like that, right? That's all CMOS RAM, and that's like 32K. Okay, and CMOS RAM, and then so those are the things that I've chosen to store in BRAM. Now, I store some of the video RAM and some of the bitmap and palette RAM. Some. I can't afford to store all of it because we're fairly limited on block RAM. I can't store all of it. So some of it. What does some mean? Okay, so we'll get into that in a minute. And then in SDRAM, and I didn't really see any value to using DDR in this situation, primarily because the reads and writes are fairly slow to it. It outputs, and you can write and out and read a fairly large amount. I think you can read about 64 bits at a time. And then there's masking, right? You can read partials of those or write partials of those and all that stuff. And it's very good for that kind of thing. But the problem is the video clock in the Y units are about 8 megahertz, and the video clock in the Z unit is 16 megahertz, right? So you're not really going to get data out at a fast rate to meet the pixel clock, right? So that's one of the bigger issues. Everything needs to be really, really fast. Like the output from the DMA custom chip has to be at a certain speed. Otherwise, what's going to happen is if it's too fast, the game will be too fast. So your bottleneck of the speed of the game is actually in the DMA chip, right? Because that's what literally draws the frames. It uses extended RAM space for some of to store some things. Like for example, in Mortal Kombat, anything after the video RAM portion of the RAM is actually used as a staging area for the next frame. So if you comment out that region, right? Let's say you restrict it so that the address bus can't write to that region. What you're going to get on the screen is a flicker. You're going to get flickers of every other frame, pretty much. Not cleanly, because some of the graphics are stored, as in two portions simultaneously, but like basically you're going to get flickering, which means it's outputting every other frame, and that'll work fine. It's just flickering, So that tells me that's used for a staging area for the next subsequent frame. Okay, so SDRAM, and then what I have there is all the ROMs. So you have the TMS, you have the audio, and you have the graphics. But the problem is I need two SDRAM modules to achieve this, because the rate at which the TMS goes and the graphics goes, like these have to be separate pipes for it to meet the timing of the actual system, because otherwise, because this graphics thing is hit really hard every single time. Like first of all, on line number 1, right? When the CRT is starting to write line number 1, DMA is already preloading the second half of the frame, and when it hits the midline interrupt, there's a midline interrupt in the system, and what that does is trigger the DMA to load the first half of the frame. So it's always constantly going really high, 32 bits every single time it does its work. And it's drawing that for all objects. It doesn't just go like, oh yes, I have all the pixels for the whole frame, I'm just going to draw them all now. No, there's like a queue. There's a DMA queue. And basically, the CPU writes to a DMA queue and subsequently sends a command to DMA. DMA then goes and draws that object. So there's like a window in which it draws it under. So the whole system is there's no hardware sprites, they call it. There's no hardware sprites in the system. It's all blitter based, right? So DMA takes whatever that object that's in the queue that the CPU writes, and it says, okay, at this location, I'm going to write 50 by 64. I'm going to write a 50 by 64 pixel window, and I'm going to use this object, right? And what that means is it's going to get that object in. It's going to start reading that object in the graphics ROM. It's going to start loading it out 32 bits at a time plus 8 for the palette ID. And it's going to keep doing that over and over and over again until it reaches the end. It's going to then report back to the CPU by triggering an interrupt. And the CPU is going to say, okay, it's done. Let's deliver it. Go to the next one, and the next one, and the next one, right? So it communicates with the CPU via an interrupt. And also it writes to registers that the CPU can read as well. And so the TMS, the audio, the graphics, and then from a RAM perspective, I have some of the video RAM, and I'm sorry, not video RAM. Yeah, kind of video RAM. Yeah, I guess I should say I do have some video RAM here, because in NARC, for example, that won't fit cleanly. 512 by 400 will not fit cleanly in BRAM. That's too high. It can only store like 256 of it, if you consider all the other parts of the system. So yeah, so I have all, I could say I have all of some of video RAM, and quite a lot of bitmap and palette RAM. Yeah, so some of those, right? And the big issue with doing that is that it's not fast enough. I mean, even with two SD RAMs, it's still not fast enough to meet the demand. It can be stable. Yeah, sure, it can be stable. In that it won't crash, because SD-RAM also, the trick about using SD-RAM is that you also need cycles for performing refreshes, and other sorts of things as well. So I mean, primarily refreshes is what we're concerned with, when it comes to SD-RAM, because if you're using it 100% of the time, it cannot go through its refresh cycles, right? And so that's a big problem, right? Obviously, from an SD-RAM perspective, and eventually it will crash. Eventually, it will just crap out, right? Um, so I've tried a bunch of different memory models, and so yeah, this is the allocation that I've landed on for now. And so NARC is not really functioning all that well, because I can't really fit all of it into BRAM. I can fit Smash TV, and I can do Total Carnage. Those two actually work very well, and I'm happy with how they turned out. They look pretty good. Now it doesn't match the speed of the original board, of course, right? Because with being inherently limited, from a graphics perspective, and also to some extent the program ROM perspective, it doesn't quite function at the speed that I like as the original board, but it is playable. So that I'm happy about. It's validation that the system, actually works out. Now, some other models that I've tried is having all of the bitmap and video. So this is two. Having all of the bitmap and video RAM in BRAM. So all of it, just simply all of it, all 512K of this will be in BRAM. Well, the 512K representation of it's not really actually 512K. It's smaller than that, but yeah. Basically, the whole region of addresses is what I mean. The whole region of addresses for bitmap and video RAM in BRAM, and then I would just do the palette RAM in SD-RAM. And what does that mean? That means that the vast majority, well, half of the data will come from here, right? So for every 16-bit read, you're actually getting 2 pixels instead of 1 pixel, right? Because 16 bits is used to represent um, a whole pixel, right? And so if you're storing just half of it here, um, then you're pretty much getting 8 bits from here, and you're getting the other 8 bits from here, right? As an example, right? But realistically, since they're all 16 bits, 16-bit addressing, you're getting 16 bits from here, and you're getting 16 bits from here, right? So you're actually for every 1 pixel that you try to read, you're actually getting 2 pixels, right? Because each one of these 8 is matching up with each one of these 8, right? And so you're actually getting 32 bits out, and you're getting 2 pixels out, right? Basically, for every one 16-bit address you read, you get 2 pixels out, and that's ideally where we want to land, right? We want to land in a place where, I mean, we obviously want to land in a place where palette RAM is also in BRAM, but like basically this is close to the original architecture of the system that I have described right over here, right? And so that would be my ideal situation, is if I were to get bitmap, video RAM, and palette RAM all in BRAM. So this way I can emulate the original architecture of the system, which is reading out 32 bits from from your bitmap and video RAM portion, and also reading out the same in two 16-bit reads from the palette RAM, and getting that out as well. But you see, the original system, like I said, the palette RAM only accepted 16-bit writes. It only accepted 16-bit writes. So the system can actually get out 32 bits from bitmap RAM. At the same time, it's actually getting out 16 times 2 bits of the palette RAM. So it can actually get out 2 reads in the same sequence as 1 read from the bitmap RAM. So that's I mean, we can't contend with that really. And it can do the writing the same way too. It can write 2 16-bit writes at the same time it's writing a 32-bit stream from DMA. So you can't really compete with that from an SDRAM perspective. No way, no how. You can't really compete with that. That's a pretty high rate. And so all this stuff really has to be in block RAM, at the end of the day, which we don't have enough of on the Mister. So then we look to other systems, such as Mars, right, where we can potentially put together a good model for this system that's more closer to the real board. And that's really the ultimate goal. Is we want to take a look at the board, and we want to basically figure out how we can implement that, as close to the actual working of the board as possible. Not only from a timing perspective, but also from a logic perspective, right? If we start consolidating things and doing all this stuff, sure, the game might work, right? It might work to varying extents, right? It may or may not be more or less efficient, right? Because like I said, from a memory perspective, I think the software emulation is better. I think software emulation is better for handling complex memory usage requirements, right? Especially large memory usage requirements, because those types of memory are very expensive. If you're talking about an FPGA, right? You can get a whole bunch of that on a PC, right, or a smaller Pi unit or something, right? And so that's where it's more efficient. Now, from a computational efficiency perspective, I mean, arguably, you can't really contend with a PC, a literal PC, right, from a computational perspective. But I think the FPGA is better in that regard because it's more efficient, right? You're basically all fully dedicated. You have a fully dedicated chip that's doing just that, right? And so I think it doesn't have to contend with other overhead and other resources. So I think that's one of the bigger advantages of the FPGA, is having a dedicated unit to do processing, on the smaller scale, or something that's for the whole core, all in one unit and one chip. The form factor is actually smaller too, right? Because if you're talking about a PC or if you're talking about a handheld, I mean you can have a Raspberry Pi that's small, but I mean you can't really contend with the size of a Cyclone 5, right? For example, you can't really contend with the size of these types of units, and also from a heat perspective and a thermal perspective, you can't contend with an FPGA as well, right? So there are certain advantages and disadvantages, but basically we want to arrive at a point where we're implementing the system accurately, right? To as much as an extent as possible. We're not going to always get perfect. Obviously, we're talking about implementing digital circuits, based on analog equivalents, right? Or we're trying to equate analog to digital, right? So we're not always going to get perfect there, right? We can try the best that we can, but certainly I think we can take a look at the speed. We can take a look at the accuracy of how, from a technical perspective, how the frames present themselves and how the game plays, the playability of it. So that's something that where we try to focus on, and so I think that where the core is now is a good start. And I will release an alpha in a few days once I have a chance to kind of clean this up and do that. So so folks can play around with it. They can load it up on the Mister and see that. I've already given it to a few people already so far. So I mean, it plays well. It's just that it's not obviously accurate, right, because of the limitations of the system. So yeah, so I hope you enjoyed all that that basic overview of the system, and so I look forward to seeing you seeing if this video helps you on your journey, if it helps you design a core or get you motivated to to tackle a core, or fills in some gaps for you. So let me know, and I'll see you soon.